Hello, Dr. Mike here. For Introduction to Computer Forensics, the topic is on forensics imaging, specifically imaging and hashing. At the time of this recording, this is topic 8 for the CIS-2808 course. This could change, so could the textbook change, so please be aware of that if this is watched later. So, imaging itself. We know that we would ever want to ever search the original suspect's drive, and we'll use hard drive, but the image could be of all kinds of things. It could be a USB stick, it could be a phone, tablet, it could be a server, but for the sake of simplicity, we're going to talk about a hard drive. And it doesn't matter if it's an SSD, if it's a spinning hard drive. In any case, we want to talk about the process of making, through a read-only channel, a forensics copy of that drive. So that's what we're going to just do. This can be done for a hard drive. Again, it can be done for a file. This both copying and hashing process, again, anything from a file to an entire hard drive to partitions. But again, before we shut down, there is the concept of volatile data. So even though we always wanted to use the copy to go ahead and search, this is what we're going to do our searches in. Search and pick through and actually look at open files, run programs, extract archives. We do that from the copy. We never do it from the original. There is volatile data that you can use. You use software to go ahead and grab. And of course, we know that as memory probably the biggest one. And so this could be imaged, but this also falls outside the fact that you need to run something on here directly. You use some sort of USB stick, memory capture device. Some of these professional devices can do everything, capture both hard disk and memory. So it's possible. We have this volatile data, registers, cache, routing tables, and so on. You can run certain commands and capture that information, so from the memory, and also the network. So that can be done from an app that might launch or run and capture network information and either copy it out again to here. It could be a text file, it could be another image file, temporary files, and so on. So we're going to focus on disks though. Just keep that in mind for the evidence collection process. And again, I may have talked about this before. But it's important to understand that there is this volatile data up here on the stack until we get down to this 5 here, which we actually look at physical disks themselves and archive media. So again, we don't want to ever use the suspect system to search for evidence. And we don't want to open or run anything from that. Again, this is where the copy comes in, or copies. Could be multiple copies of this. And for preparation, again, they consider using solid state data to store and collect data. SSDs here on this side will be good if you have an SSD on this side too. Actually, that's actually the good news about SSDs, even on suspect side, is speed. This process is very slow. It is a bit-to-bit copy, and there are several tools to do it. And I'll show you. I'll actually demonstrate one open source tool called DD. There's some other ones you'll see in the lab. I forget the actual name. It's like LSFCDD. And it actually has more built-in, more robust features, but at heart it is DD. And but using this process is very slow. So solid-state drives are going to really make things quicker. Now, important thing too is the copy itself. So you should have an inventory of blank drives. And we're going to talk about the fact that you can actually create a hash for an empty drive. You should be able to get a hash value for that. Let's put a hash mark there. And we can use that hash value for a known blank drive and verify it's blank before it's put up here and copied to. So this whole process goes beyond just the copy of the drive. It's also verifying that the drive has been zeroed out. And a lot of forensic software tools do this. And of course, the larger forensics teams are our tool sets we'll see here and the slide deck that do a lot of this work for us. In fact, this is one of them. So a mass store, a disk analyzing system. These things can, wipe and hash the target drive, and then through a read-only channel, hash and do a copy to that drive. So it all can be self-contained. Very fantastic, these toolkits for preparing and creating the copies. There's both, these can be travel. You see here, this is a field kit. So this can run with a field kit. Comes with a nice Pelican case here, it looks like. With several connectors. That's the thing too, right? We don't know what the connector is here. Is it IDE? If it's SSD, it's, it's probably, it's a SATA drive. But you have all kinds of connections. USB Mini, USB-C, Thunderbolt, IDE, SATA. There's the P SATA. There's just small SATA connectors. eSATA. That's the one, eSATA. So we have a lot of connectors here. So you can imagine this toolkit's going to be stuffed with connector adapters. So, but you're not sure what you're going to run into at the final destination. And of course, multiple empty verified blank drives, more than one. Always want to have backups. Even backups of these actual devices. You might have 2 of these for a mobile kit. So again, very important we collect the snapshot of memory and so on. And then I'm not going to talk about that here, but it's very important to get this sort of picture of the entire system, including the date time of the BIOS before it's shut down. So it could be just usually you can do a screen picture. Usually we'll do an image on a valid imaging device. It's like a digital camera. So again, I'm talking about the shutdown dilemma. If it's up and running, you leave it running, you shut it down. If it's a mobile device, always grab the charger with it. If you don't have one, you should hopefully have a bank of chargers back at the lab. If no charger was found, the original charger, if it was plugged into it. And again, we document everything from the scene, exactly how it's plugged into what before we take it apart and change it. So let's actually focus down now on this process of doing the bit-to-bit copy. And we can do a couple of separate things here. So first off is we're not doing an actual copy. We're not using like a copy command or xcopy or using a backup program. We're actually doing a forensically sound copy using an example DD. So, but we can copy certain things. So a full volume copy is definitely the best, but it's the slowest. So if we have a duplicator, we'll do this. A lot of duplicators will actually have built-in tools like WinHex and so on, built-in hashing, and we'll come to hashing in a second. But a bitstream copy is, again, forensic duplicate. Think of it as a bit-to-bit copy, every single byte from the disk. So you can imagine a 4 terabyte hard drive can take several hours, extensively long, 8 hours, 10 hours, to get an actual bit-to-bit copy. So time is definitely of an essence, and time can be an issue. And then, of course, to actually get a verifiable image, you have to go and hash it. Hashing can take a while too. To hash an entire 4 terabyte drive can run for a long time. So there are options here we'll see where you can take partition copies, and we'll come back in a second. So, but again, we have our original copy. So if we look at the actual textbook here, we talk about forensic imaging, and DD is really one of the first things you run into, and talks about DD here. DCFLDD, that's the one I was talking about. That's actually the more Defense Computer Forensics Laboratory DD command. There's a DC3DD and so on, and there's actually other tools that will actually create forensic images and create encase images and other tons of tools, both commercial and open source. So now, of course, hashing is an important part of this. So what is hashing? Think of hashing as the digital DNA of whatever this is. This is a hard disk. Is it a partition? Is it a zip file? Is it a single doc file, or or JPEG? All these things will create, using a hashing algorithm, a unique signature. So think of this as the DNA, digital DNA. And we'll actually demo this here in a second. Now, how does it do it? There are several things we'll see. There is MD5, Messaging Digest 5, and I'll demo MD5 because it's quickness, but I'll talk about what it is in a second. Then there's, of course, the SHA series, SHA1, 128, 256, 512, and so on. 512, SHA series. And what this is the cryptographic algorithm. So I'm not getting into the mathematics of it, but for example, we'll pick MD5. Now off the bat, if you look up MD5 and you look at it for cryptography, it is definitely invalid for cryptography. It's too weak. It's a weak for cryptography, but it's good for image integrity verification. So it's still used for this a lot. And what we'll see is several tools will actually produce MD5, SHA1, and SHA256, even 512. It'll produce all the hashes at once. So it's not uncommon to have actually multiple hashes. And it's actually recommended not just to have single hash, but have several hashes from several hashing algorithms used. So in essence, it's a mathematical process of preparing the target and breaking it down into 512K blocks, and these 16 32-bit word blocks, and then using padding where needed, and then breaking that into a 64-bit table, and it gets pushed through several. We have here is these are XORs, which is the little XORs, ands, ors, or nots. So basically, it's some basically basic logic tables, some basic sort of basic binary algebra we have here. And again, I'm not going to get into the mathematics, but it produces an output. And the output, we'll see here in a second, looks like something like this. It will be a MD5 number. They have an example and they don't. We'll show you an example here in a second. So MD5, again, if you look it up, it says it's not really good for definitely for any kind of cryptography. It's too weak to use to hash passwords and so on. So there's things about hashing. It should be a fixed size. It should produce a unique result. Unique result in a realistic unique result. So what that means by that is there's some called collisions. And for MD5, there is some possible collisions, which means I have, let's say, two documents here, totally different documents, but they produce the same MD5, which they shouldn't. Now it's pretty uncommon, but there's even an example here of two MD5s that are actually different. The bits are different, but actually produce the same. Here's an example MD5 hash. But produce the actual identical MD5 hash. So this is why you'll see a lot of tools will produce multiple hashing. Now SHA1 is a longer hash. It's a longer process, so there's less collisions, and you can probably guess 128, 256, and the 512, very long hashes. So good to have multiple hashes to really show the integrity of your file, or show that digital DNA of the file. So, and again, we compare off the original suspect's device. We get a hash number, and it should equal the hash number on our copy. And that proves it is unique. And I'll demo that in a second here. So again, I don't want to get into the mathematical depths of MD5 hashing. Where you might see MD5 though is if you ever download an ISO image for like a Linux, for example, or any kind of file. Sometimes you might download a tar file, tar GZ file, or even from Microsoft, maybe an ISO file for Windows 10. Then they'll provide a checksum, they call it, or an MD5, and that allows you in this example here to download it and run through your own checksum, which is called checksum, or your own MD5 sum, and you can match them and say, yeah, it is. That way you know you have a, it is 100% the image that was downloaded. But you don't want to download a operating system and find out that there's a couple bits that are wrong, and then of course the install will fail. So again, historically, MD5 was used in one-way hashing of passwords. Again, not anymore. It's not recommended. But again, it should produce a unique output, and also that output can never be normally for encryption reasons should not be able to be sort of used to determine what the original message was or what was changed. So there's some things around integrity hashing, the depth of it here, and this is the textbook will go into a little bit of that. You can see there's 256, 512 mentioned here. You can talk about the length. SHA-1 is 160-bit. MD5 is 128-bit, so the longer the hash, the better. And talks about hash collisions in here. So, again, let's go back to creating our copy. Again, copying takes a long time. Full volume copy takes a long time, and even hashing a full volume can run for a while. So, a couple things here, tips: make sure you get the date time from the BIOS. Remove any storage media before powering on, to check the BIOS and so on. So in other words, you take your image, shut the machine off, you pull out the drive, you turn it back on again, you go to the BIOS screen, you get your BIOS date time. That can be important because those date times you'll see later, or may have seen already, are used in computing the file date times. And again, document everything. How it was created, who did what, and if it's evidence, it gets bagged and tagged appropriately. So this talks about HPA areas. I'm not going to go into that here, so we'll move on from that. Again, and this applies to cell phones, iPods, iPads, so on. Any personal device can go through this process for both memory and hard drives. So again, you might only extract certain things. For example, we only need certain aspects to be extracted from a device. If it's a cell phone, we might want text history, maybe phone books, GPS information, and so on. So when it comes to collecting hard drives, especially large hard drives, you can do something called a partial volume image. So, for example, we know that we just want, based on the case, you might be directed to say, well, we're looking for images, and we're looking for username of so-and-so. Looking at the boot record, and then we can find the Windows, there's only one OS image. We find the OS partition, and there's only, we can extract in the registry, and see there's only one user who's ever been registered, and then extract just that user's home directory. And even that, let's extract the user's home documents, maybe, or just the home directory. So that's going to limit the scope of the extraction. This is called a partial volume image. And it's going to help you get a quicker image to find evidence faster. Excuse me. So again, there's pros and cons for that. Chances are you might take a partial volume image right away, and later on do a full volume image. And look at those temporary files and boot registries and so on to maybe find some hidden stuff. So again, important thing here is there is the NIST standards that can be used for forensic tool testing, and it's important these tools are used, whether they're like we saw the mass store images, those mobile forensic toolkits and so on, are both tested and verified, and we see there's actually a testing guidelines posted here. So okay, let's actually look at a example here for imaging itself. Okay, so here in my downloads, you can see we have a USB drive DD image. So we'll go and use that as our example. So the command itself is pretty straightforward. DD, and I'm choosing the basic DD command. Has a couple parameters, and I don't get into all the aspects of this, but IF is in file, OF is out file. So in file being USB drive. I'll make a USB-copy DD. There's something called BS for block size. If you know the block size of the original image, You can increase the speed by increasing how much it grabs, because it's grabbing just this entire blocks at a time. If you're not sure, the default's 512 K blocks. If I just do it like this, you can see here it was done. You can see we have those two drives now. Now they match in size, but of course the date time is different. Now again, so if I sh, let's do a MD5 sum of USB drive. And we can see here we have our USB MD5, and we'll do the same thing for USB copy. Oops. And we can see these match. There you go. That's good right there. So that proves with MD5 that this is an exact match. Now, to verify this hasn't been tampered with, no one's tampered with it. Let's go and actually do this. We're going to mount we're going to find it. There you go. All right, we're going to mount this copy. So sudo mount dash option is loop home Sans Forensics downloads and USB copy, and we'll mount that to home Sans Forensics image. All right, so see here we mounted a copy of it. So if I go in here and tamper with the evidence, let's go and open this file. And the ringleader is Dr. Mike. That's not. It's Dr. Bob, let's say. We'll save that. We'll close it. And we'll sudo umount. Okay, so unmount the image. So again, let's look at what we have here. So again, these are the same size. So can we assume they're the same? Let's go take a look. So again, let's run through, and we're going to MD5 sum our original drive, the original MD5, and we're going to MD5 sum our copy, and it's not. You can see it's completely different. So even that small change in the evidence, now this has been shown not to be a forensic exact copy. So that's a really simple test there, simple demonstration, but hopefully it comes across and shows you that any small change inside of what this image was, because of the way hashing works, even though the file size did not change, we can't assume it's the same. In this case, we can see the MD5 has changed it. So that really wraps up just a quick demo about the importance of the imaging process and some imaging tools, and even more important, the importance of creating our hashing using a hashing algorithm, using more than one. MD5 being one of them, as in this demonstration, but again, SHA 1, 256, and 512 being more common. And again, you'll see multiple, and all this stuff will go into, of course, any notes that will then end up being in a final report. So, anyways, that wraps up this topic. I hope this is helpful. Thank you.